GRPO, Group Relative Policy Optimization, is one of the most popular learning techniques right now. It works in style of reinforcement learning where the rewards come all over the end, all over at the end. So for example, if you have generated long trace program and you an annotator tells you that the program is correct or it needs some fix, the reward comes all the way at the end, and you want to learn from the reward and fix the trace generation or the program generation. So what's the basic idea? Basic steps. You generate, instead of one, you generate multiple traces or rollouts, and for each of these traces you get a reward. From the reward you get these relative advantages. I'll talk more about that. And once you get these advantages, you can think of them as rewards for now. You compute the gradients on the parameters, and then you take positive gradients to promote the traces which have higher advantage, and you try to demote the traces which have lower advantage. So this is how for each trace response there is a reward, and it's automatically generated. So that's why this RLVR, reverse learning verified rewards. There's generally an automated technique that generates a reward for a trace. For example, you can say the program is correct or wrong, and um, and from that reward, you don't use this reward directly to compute the gradients. You instead compute an advantage for it, and this is where the crucial differentiator of this is the crucial differentiator. The idea is that you compute the mean of the rewards, and then you compute the mean and standard deviation, and then you essentially if your mean is if all the rewards are similar, then you get a very small advantage. Whereas if your rewards are highly dissimilar, then you get a large advantage for both good and bad traces. Okay, so that this advantage is a key idea that makes GRPO. Essentially, it allows you to learn from good and bad traces more efficiently. Okay, so the full GRPO objective depends on a number of factors, and it's not just the advantage, it's a couple of other things that are meant to stabilize the training. The full GRPO objective consists of not only the advantage but also the scores of the traces with respect to the current model that you're training and some slightly older model. It, there's also a clip component that prevents the ratio from going too high or too low. Then there's a KL Divergence term which compares the scores with the current model and an older reference model. Okay, these scores are essentially log probabilities over the whole traces, which can be computed from individual probability scores. Okay, so the full formula of this, which is pretty intimidating, well, you can see that as this ratio multiplied by the advantage, and other term is clip. It tries to make that ratio within the 1 minus epsilon plus epsilon range. So it's a minimum of these. So if the ratio multiplied by the advantage grows too big, then the clip term will be taken, and then there's KL divergence term. So to understand it better, we can see the equivalent code for this, for the code part of this formula. Essentially, there are two loops. We have a bunch of generated answers, responses, and the reward for it. And for each of those generated answers, we compute the advantage, this formula A minus mu divided by standard deviation. And once you have the advantage, we use the advantage to compute a token loss for each of the tokens generated. Pi theta is the individual score. So once you have token loss per token, then you sum together losses divided by the length of the generated answers to normalize it. So we get the loss of each answer. finally we get a final loss for the whole group is sum of the all the losses divided by the length of the generated answers. Right, so this is the core loop of GRPO, and to understand why we need importance sampling, uh, we, this is where the problem is. Essentially, the idea is that when we compute these gradients over the loss or multiple iteration, then it goes off policy. So the new weights after updating are different from the ones that were used to generate the original reward. Okay, so you generate these rewards, compute the gradient based on those rewards. After you compute the gradient, the model parameter is different from the ones that were used to compute the original reward. So it goes off policy. That's what's called off policy. And essentially, the training sort of diverges from the supervision, which is the reward. And ideally, we would want it to um, for every advantage computation, you want it to immediately update it and then regenerate the group of responses, but that's very costly, expensive. So this is this trade-off to compute a bunch of traces, compute the advantage, and use it to update the parameters for multiple iteration introduces this issue of stale data. Okay, and to solution is the ratio. Essentially, it keeps track of the original pi old, pi theta old related to the pi theta which is updated. And if the pi theta doesn't diverge too much, then we keep the same advantage. Otherwise, if it diverges, then uh, we multiply, we scale up the advantage by the amount the current scores differ from the original score. Okay, so the issue is that this ratio, and this is the second part of the full equation. This importance sampling ratio could itself get unbounded, depending on how much the new scores diverge from the old one. And so we add this clip part, which binds it between 1 and minus epsilon and 1 plus epsilon. And so those are the three key parts, or two key parts of the GRPO. The other part is KL divergence, which is yet another way to force the new model to be closer to the older one, not diverge, make it diverge too much. But research has found that if we add this clip term, then we don't really need the KL divergence. So essentially, uh, these two terms, the minimum value of these two terms is what goes into the loss. Uh, and the KL divergence term doesn't matter. Okay, so that's um, the core components of the GRPO equation. And there are many optimizations proposed on top of this basic GRPO. For example, you only consider forking tokens, which are crucial tokens like but or well, which determine what the next step of reasoning will be like, uh, what would be the reasoning, and what would be the reasoning argument. So if you can just focus on these forking tokens and have the same, you get the same losses and the gradients. Okay, so there's several optimizations which I'm not going to talk about. I'm just going to revisit the core differentiator idea, which is uh, these advantages. So this is a quick calculation of how there are three responses generated, and the rewards 0.8 for this one, 0.5 medium for this one, and about 0.2 which is a low reward. And so instead of using the reward, if you compute the mu, and divided by with the z-score, r minus u divided by z, sigma. Uh, Find that the advantage first one is plus 1.22. The second trace is closer to the mean, so it's 0. You don't really learn from this. And A2 is to discourage. You get a minus 1.22. So this is really interesting, and this clearly illustrates the advantage of using advantages. The idea is that you get to learn from both. You clearly differentiate the positive and the negative traces. Okay, so if you look at the rewards, it's not very clear, but uh, having a mean forces clarity among the traces to learn from, the good traces and the bad traces. And so you can get the good gradients from here and the bad gradients from here and use it to update the parameter. So it's sort of contrastive learning. If you have a group, the group helps you collect a bunch of traces, learn from them together. And on top of that, advantage helps you distinguish the positive and the negative traces and learn from them more efficiently. So this is one of the reasons why GRPO based RL is superior to SFT, standard supervised fine tuning, because it has a form of contrasting. I'll call it just contrastive learning directly while generating the traces on the fly. The other thing is that the traces generated on the fly relatively, I mean, you have these batches of traces, a group of traces, and then learn from them and generate another one, as opposed to standard supervised training where you you have a bunch of traces generated offline, and uh, during learning the data becomes stale. The model keeps changing, the parameters keep changing, and the rewards that are associated with those offline traces do not hold in the with the current model. So the learning gets a little bit um, off track. So yeah, so a couple of advantages here, and that's why GRPO has become very popular, especially in the verified rewards, where you have a mechanism, a evaluator function, which can give you precise rewards. I'll be talking more about the impact of RL on reasoning, improving reasoning abilities, and other recent developments. So stay tuned.